So this refers to simulation of river flows, and in particular it's assigned, it's given a cross river section. Let me see if I can increase. Not really the grade. Yeah, let me see. Just 1 second. Okay, so it's given. So basically, it's a river cross section is given, for which we have river flows data at daily time scale for 5 years. And you can download the river flows at that web address. And let me select it. Oh, sorry. And it is required to estimate the flow duration curve with uncertainty analysis. Uncertainty analysis means that you have to estimate not just the mean flow duration curve, but not just the flow duration curve, but also its variability. You may remember yesterday that I introduced two procedures for estimating the flow duration curve, and the first one that I introduced yesterday allows you to estimate also the variability. So basically here uncertainty analysis means that you have to estimate also the variability. So we have to use the first procedure. And then in order to do that, in order to estimate the flow duration curve, it's written here that one is required to generate a synthetic series for an observation period of 50 years. And in order to reach the above goal, it's written here, it's required to draw a graph of the original time series. This is analyze the time series by assuming that both mean and standard deviation are seasonal. You just have to apply the procedure that I introduced yesterday. Estimate an AR1 model to the data. Check that residuals are Gaussian and not correlated, and that there is written skip the check on cross correlation. We didn't mention the check on cross correlation, so you just have to ignore it. Generate the required synthetic series, estimate the required flow duration curve, and then there is written explaining a brief report the above elaborations. This is not really necessary. Okay, now the next step, if you don't have any question, is to download the data. And let me try to go back to the I need the menu here. Okay. Just 1 second, I'm just trying to get back to the visualization. Can't understand. because it's possible to get the link from here, but not for me. Okay, finally I got it. Okay, so I'm now just copying the link from here, and it's possible if you visualize the PDF on Adobe Reader. No, it's not possible because, yeah, you're right, it can be saved. Okay, so let me go back to, so it's files, data, river flows. I go back to my home page, and there is no other solution than sorry, it can't be saved, but anyway. Files, data, river flows, let me see. Site, okay, I forgot this. Okay, here they are. Yeah, sorry, you have to manually enter the link in the browser. And let me see if there is no link from the website. I'm curious. I don't think so. No, you have to manually enter the link. Sorry for that. Okay. Now, next step is to upload this data in R, and to do that, my preferred solution is to select all the data. Sorry. And then with Ctrl+C, I copy the data in a notepad or whatever text editor. I use this one, here I have the data, and then I save the data on my desktop. So basically you have to select the data, copy and paste the data in a text editor. You can use Notepad. And then save the data from the text editor to your desktop. Or save the data in a position from where you can get the data from R. Okay? If you have any problem, just let me know and I can explain to you. Okay, good. Now, next step is to download the proposed R code for its solution from my website. As usual, this proposed code is something that is given to you to facilitate your task, but ideally you should try to understand whatever is it's done here. Here is the code. And the code is well organized in a way that if you just cut and paste the code in R, you get everything done in 1 second. So this is of course not what we would like to do. And in the next hour I will go through each of the instructions one by one. But in order to make the whole procedure easier, I will copy and paste from here. But I will comment any instruction to explain to you what's going on. So I keep this page, which is just a web page, from where I can copy. And then let me open a console and open R in a position, of course, where I can upload my data. So 1 second. I open R here. This is my document with the data. So, okay. Okay, here it is. I am ready to start in R. If you are ready, just give me a sign. Are you ready? Can I move forward? Okay, so I go back to the web page, and then you see there is written load the data and make the plot. So I just make a selection of the first 3 lines. You see that the first line is commented, doesn't produce any effect in R. The second line is a scan instruction to upload the data. Given that the data are given in a text file with no lines to skip, I just can give the instruction to scan it, and that's it, because there are no lines to skip, as I said, and also the data are in one column, are displayed in one column. And then the third line is the plot of the data. It's a very rough plot, but just to see them. So let me go in R now, and I can just paste. So, okay, because it's wrong the path. So let me go back. You see this path here is wrong. I just have to, yeah, because I didn't call it river flows, but I call it data. Done. Of course, this is always a delicate step, so I would prefer to wait that you uploaded the data yourself to get a confirmation that you are ready. Basically what I did in my case, but again in Unix I just used data scan data txt. That's it. But you see that I made a couple of mistakes because I didn't give the right path to R. It's always a problem, and especially in Windows it's a problem, because if you put the data on the desktop to give the path of the desktop, it's not easy. You don't have the connection, so I can give you a USB stick if you want. Do you have it? Okay. Please. It's called data.txt. Okay, that's fine, no problem. So, who was successful already? Were you successful to upload data and just check? Same problem. And what about you? You are fine. Okay. Yeah.
Why we paste the first three lines?
Yes.
Because also.
You missed them.
Huh?
So.
No, I don't understand why we paste in R the first three lines of the R code .s.
Yeah. First of all, no, I needed to replace to correct them just to give the right path. That's it.
Mm-hmm.
And did I reply to your question?
Okay.
Okay.
But so we don't need them.
Yeah, you don't need to write C dot
Yeah.
/ etc. You have to give your own path.
Yes.
Okay. I'm just waiting when you are ready. And you are ready? Everybody's ready? Okay, good. Okay, let's now make the plot. Sorry, I go back to the console. This is the plot. The reason why I suggested to plot the data, I think I already mentioned to you this, let's say, good practice. It's that when you start analyzing data, it's always a good thing to start with the plot. Because if something goes wrong, you can realize it. And what can you realize by looking at the plot? First of all, if there are outliers, if there are missing values, and sometimes from the plot it's evident. So this is the first assessment that we should make. And then you can also look at the data, and if you have experience, you can judge if the data provide a good representation of the process. If you don't have any experience, looking at the data, you build your experience. So this is a river flow series. And basically, what can you see looking at this graph? You can see that there is a strong seasonality. It's clearly visible because these are 5 years of data, and you can see that there are about 10 periods of high flows. If you count the high flow periods, they are about 10. And this means that you can clearly recognize a seasonality, and it's a seasonality such that you have 2 high flows period within the year, which is not always the case, because if you have a climate which is dominated by monsoons, you just one high flow period. Two high flows periods are typical of the continental climate, of the European climate, and the mid-latitude climates in general. So this is something that you have to learn to recognize. Another thing that you can easily see here is that there is a significant variability that is superimposed to the seasonality. This is not always the case. If you look at the flow data of the Nile River, you see that there is a very strong seasonality and the variability is a small thing if compared with seasonality. In this case, you have a significant variability. Also, you may check that you don't have negative values. And in general, look at it and try to understand everything that you can see. Okay, in any case, by looking at this graph, one may say that it seems that everything is going fine. Another thing that you can realize is that you don't have any evidence of non-stationarity. This is another issue that you should try to clarify as soon as possible when you deal with data. By looking at this figure again, you don't see any clear evidence of non-stationarity. Of course, there might be some hidden non-stationarity, but then it's not so significant. You know, in this case, you don't see any clear evidence. Otherwise, you may have seen, I don't know, a plot like this. Let me make an example. Let me see the data, 800. Sometimes you see a plot like this, data plus. I'm just drawing an example now. Let me see how it looks. This is too much, but this is an example of non-stationarity, okay? This is too much. Let me see if I use 0.2. Okay, no problem. This is still too much. In any case, if you see an increasing trend, I wanted just to display a less increasing. This is clearly too increasing, but this is an example, evidence of non-stationarity. Okay, let me go back now, and let's move forward with our exercise. Now, what we have to do is to compute the seasonal component. And the next instructions here, you don't know them, so you have to pay a bit of attention. Let's move forward one by one. First of all, this one here, which I'm copying and pasting in R to explain to you what it means. So basically, what is the function TS? Is telling R that the data are a time series. TS stands for time series. And basically, the TS function wants as arguments the data vector from which the observations should be taken. And in this case, I used the same data vector. You see that I am overwriting the data with another definition of the same vector data, just in order to keep the memory of the working session clean. But you could use a different vector. You could write there data1 is equal to TS of data. And then the frequency. The frequency means if you have a periodicity, you should tell R that you have such periodicity. In this case, they are daily data. The frequency is 365. If they were monthly data, the frequency would be 12. If there was no periodicity, the frequency would be 1. Okay? In our case, of course, frequency is 365. You may say that this is not the frequency, it's a period, and I would agree with you. But anyway, if R adopts this representation, let's of course adapt to it. Okay, so now we told R that this is a time series with a periodicity of 365, and you may guess that this is instrumental to computing the seasonal component. Indeed, R has a very useful function to compute the seasonal mean and seasonal standard deviation. You may remember yesterday that I introduced this technique for the seasonalizing the data, which requires computing mean tau and sigma tau. Okay, so let's compute them. It's very easy now. I go back. First of all, you need this instruction. Let's see what happens with it. Okay, so what is this PR1 that I defined? Let me show it to you, because the simplest way to understand what the function cycle does is to see its result. You see, it's a series of indexes from 1 to 365, which is as long as the original series of data. So again, this is the instruction. PR1 is equal to cycle data, and cycle just gives back the indexes, which is useful because you mark each observation with a number that allows you to identify the day in the year in which the observation was taken. Okay? Okay, just stop me if something is not clear. Then the next function, I define two variables, which I called says mean and says standard deviation, and these vectors, which I just defined, are the vectors of mu t, mu taus, and sigma taus. So let's see how I computed them. I used a function which is called the apply, which applies to the data. You see, the first argument is data. The second argument is the index, which identifies the day of the year. The third argument is the function to compute, the periodical function to compute on the data. The result of these two applications of apply is a vector which is 365 long. And precisely, they are the vectors of the seasonal mean and seasonal standard deviation. Which is what we need. Now it's very easy to compute the deseasonalized series. Let me go back. First of all, you see that to get the seasonal standard deviation, I need to take the square root of the seasonal variance, because what I computed is the seasonal variance indeed. So let me take the square root of it. Now, let's see these two instructions. Data d, I am defining a variable, a vector which is called data d. Data d is given by data minus, if you look at the screen, I'm reading there, data minus the repetition of the seasonal mean up to a length that is the same length as the data, The result of the difference is divided by the repetition of the seasonal standard deviation up to a length that is the same as the data. This instruction that is written here is nothing else than the application of the relationship that yesterday I wrote in the blackboard to compute xd. You may remember I defined the variable xd. So basically this relationship that you see here is nothing else than that. Okay, and now the plot of the deseasonalized data. Here is the plot, and if you compare the plot with the previous one, first of all you may see that the data were scaled, and this is to be expected. I told you that the resulting deseasonalized series has zero mean, and probably I didn't tell this yesterday, as a standard deviation of 1. Because if you divide the data by their standard deviation, you get to a standard deviation of 1. So you don't see any more seasonality here. This is the other striking feature that you can get from the plot. Okay, there is another thing that we could do at this stage, which probably is not included in the code. Let me see. Yeah, it's not included in the code. At the beginning, when you plotted the time series, I told you that it was quite clear that it was seasonal. If you want to get a confirmation that the time series is seasonal, a good solution is to plot the autocorrelation function of the data up to a lag which is the same as the length of the seasonality. So up to a lag that in this case should be 365. Why is that? Because seasonality is equivalent to the presence of memory between the observations that were taken in the same period of the year. So basically, seasonality implies that any observation that is collected in January or January 1st, in a specific day, is dependent on the same observation of last year. Not because there is a real memory, but because they have the same order of magnitude, and therefore you see a dependence. So the autocorrelation function is a very useful indicator of possible seasonality. So let's try to plot it. ACF data lag.max equals 365. Lag.max is a parameter that allows me, an argument of the function that allows me to specify the length of the maximum lag to which I want to compute the autocorrelation function. So let's see what happens. If I go in the plot window, you see here what happens. This is clearly an autocorrelation function that tells you that there is seasonality. First of all, look at the ordinates. You see that they vary from minus 0.2 to 1. And at lag 0, you have an autocorrelation coefficient of 1. This is fine. And also look at the abscissa. It's up to 1. 1 because it is a time series and R recognizes it and therefore doesn't plot to you the lag, the actual lag, but rather the progress in the seasonal cycle. So 1 for it is 1 year. Okay? And now let's look at the autocorrelation function. What do you see? You see that indeed there is a first initial memory up to a lag of about 0.1, which means more or less 1 month. Which means that the river by itself remembers its past for an actual memory, for the presence of an actual memory, for about 1 month. And then you get after 1 month to a condition of memory that is close to 0. And then you have two peaks. One is for lag equal to 1 year, which is explained by the consideration that I made before, that observations collected in the same day of the year have the same order of magnitude, and therefore it implies an effect like a memory. This is, again, not an actual memory. It's due by the fact that the order of magnitude is preserved by seasonality. And you have a similar effect after 6 months. Why is that? Because this is a climate with two peaks in a year. So you get the same order of magnitude for river flows after 6 months and after 1 year. And then you have two minimums. The minimums are negative memory. And you may remember that negative memory means that when you get to an high point, then the subsequent observation is a low point. So you have up and down. And this is what happens indeed after 3 months and after 9 months. Because when in the climate you have two peaks, you have also two droughts. So when the delay is 3 months, you get the connection between flood and drought, which means negative memory. And the same after 9 months. So the autocorrelation function tells you a lot of information, physical information, actual information. It's not just a statistical nuisance. Now, what would you expect from the decisionalized series? Of course, we would expect not to see any periodicity in the autocorrelation function.